Okay, welcome back to Calculus. We're going to finish up our work in section 7.8 and actually our work in chapter 7 by talking about one more kind of improper integral, a so-called type 2 improper integral. So I'll tell you what I mean by that below and show you how to handle them and some examples. And then I'm going to show you something called the comparison theorem. It's a tool that allows you to determine under certain circumstances whether an improper integral converges or diverges. And it's kind of setting us up. It'll creep back up for us in our work in chapter 11 when we look at sequences and series. We'll have a comparison theorem there as well. So this thing is kind of setting the stage for that. But it's an interesting tool in and of itself. All right, so let's get going. I'm going to start by looking at just an example. I'm going to motivate this by looking at an example. So I've got a function. It's 1 over the cube root of x. If you prefer to write that cube root as a power, I think that's a good idea. It's 1 over the 1/3 power of x. And I'm looking at the integral of it from 0 to 1. And this integral, I need to say something about it because without saying something, this thing isn't quite defined because there's a value of x, namely x equals 0 for this function, for which my integrand is not continuous. It's not defined there. So way back in chapter 5, when we developed the definite integral, the Riemann integral, it was required that the function that we're integrating be defined and continuous for every value of x between the upper and lower limit of integration. And this function is violating that. Yeah, this function is not continuous at x equals 0. So y equals 1 over 1 x to the 1/3 is not defined at x equals 0. So this integral isn't defined. Okay, so here is the kind of big idea that we're going to take to handle such things. I'm going to pick a value of x. I'm going to call it t, just like the book does, somewhere bigger than 0. So I'm drawing it in my picture there. And now this function is defined perfectly on the interval from t to 1. So I'm shading that red there in the picture. So what makes perfect sense from chapter 5 is we can integrate this thing from any number t up to 1 over x to the 1/3. Yeah, and then what are we going to do? Well, we'll just take the limit as t approaches the forbidden value 0. And in this particular case, I have to say it approaches 0 from the right. It's a one-sided limit. So you might want to go back to chapter 2 and review that limit notation if it's unfamiliar to you. So this is how I'm just going to define, write it over here. So I'm going to define this integral. This integral is not defined as it was in chapter 5 because of what we said, that there's a point of discontinuity. So when I see something like that, this is the definition I'm going to make for it. Integrate from t to 1, work out the answer as a function of t, and then let t approach that left-hand endpoint from the right. All right, so let's go ahead and see if we can finish the calculation here. So I'm going to use careful limit notation. This t is going to 0 from the right, and then an antiderivative for x to the minus 1/3. Well, you have to add 1 to negative 1/3, so that's 2/3. Then you have to divide by that new exponent, and I'm going to evaluate that from t to 1. So we're almost about to look at the expression that we have to take the limit of. So I have 3/2. Plug in 1 for x, and you get 1, and you plug in t for x, and well, you get t to the 2/3. Yeah, and now there's only one t in this expression. It's right here, and as t approaches 0 from the right, its 2/3 power is going to go to 0. So this term is just going to go to 0, and so what we're going to be left with here is 3/2 times 1, or just 3/2. Okay, so that area of the region, it's an unbounded region in the sense that there are points in this region whose y coordinates are arbitrarily big. Yeah, that thing has a vertical asymptote. The graph never crosses the x-axis, but the area in it converges to a number, and that number is 3/2. So we're going to use the same language. I'm going to say that this integral, which is improper because of the fact that it's not defined for some point in the interval of integration, namely at x equals 0 for us, we're going to use the same language and say that this thing converges to 3/2. Okay, and I'll interpret that as the area below that curve between 0 and 1, even though, again, that area is an unbounded region. It's an infinite region in the sense there are points infinitely far away from the x-axis in it, but its area is 3/2 square units. Nice. So let's look at some book pictures here. I just did one of these. These things are called type 2. I hope this is big enough for you to see on the screen. You can look in your book where I got this if it's hard to see. Type 2 integrals, improper integrals, what makes them improper is that they have a point, either a left endpoint or a right endpoint of the interval in this slide, for which the function isn't defined. So let's just look at part A here. The author's saying if f is continuous on A to B, but not including B, can your eye see that? So it's continuous on the entire interval except for the right-hand endpoint. It's discontinuous at B. Then by this integral from A to B of f of x dx, the picture that the author is drawing is right here. You take a value of t, less than b, and you integrate, watch where I highlight when I say this, you integrate from a to t. And then you take the limit of that as t goes to b from the right, or excuse me, from the left. T goes to b from the left. Down here in the second picture, maybe I should have started with it because it's like the example I just did. There, your function is continuous everywhere except for the left endpoint. So by the integral from a to b, you mean integrate from t to b for any number t bigger than a. That's what's written right here. Integrate from t to b, and then take the limit as t goes to a from the right. All right. So these things are both defined in terms of limits. And in both cases, what we're doing is we're kind of cutting off the part where the function isn't defined, integrating over the resulting interval, and then letting that point that we cut off approach the point where the function isn't defined. So on this side, we would be taking, let me write it in a little bit bigger font so you can see it. We're going to take the integral from a to t of this function f of x dx, and then we're going to take the limit of that as t approaches b from values that are less than it. Down here in this picture, we're going to take the integral from t to t to b of f of x, and then when we're done, we're going to let t approach the number a, and here it's approaching it from values that are bigger than it. Okay, so that's how we're going to treat these things. Let's look at another example. Type 2 improper integrals are a little bit sneakier than type 1 improper integrals because you might not notice it. It looks like a normal integral, right? It doesn't look improper. You have to look at it a little bit more carefully. Here, it's once again, the lower left-hand endpoint is my problem. The lower left-hand endpoint is a place where the function isn't defined. So I have to recognize that, and then I write, okay, so we're going to take the limit as t approaches 0 from the right of the integral from t to 1 of 1 over x dx. So that's using the definition that we just did above. Okay. So how do we do that? Well, we're going to take the limit as t approaches 0 from the right of the antiderivative. Sorry about that. The antiderivative evaluated from 1 to t. The antiderivative of 1 over x is log of x. Okay, so that's what I'm plugging in. So I'm going to take the limit as t goes to 0 from the right of the log of 1 minus the log of t. Okay, the log of 1 is equal to 0. So that's the limit as t goes to 0 from the right of the opposite of the natural log of t. And you know from properties of logarithms that as t goes to 0 from the right, the logarithm goes to negative infinity. So that minus sign is giving me infinity. So I'm going to write up here that the integral from 0 to 1 of 1 over x dx diverges. When the limit doesn't exist, it diverges. Okay. Let me sneak in one more example here. I'm going to just call this, what was that, example 2? Let's call this example 2.5. How can we look at example 2.5? Let's try to do something like the integral from 1 to 2 of 1 over, say, x minus 2. All right. So I just wanted to do a quick example where the problem here is not the lower end point, it's the upper one. Yeah, the function 1 over x minus 2 is not defined at 2. So it's the upper limit of integration that's the problem. So when you do something like this, we're going to take the limit as t goes to that upper limit, and we're coming into values that are less than 2. So it's a left-hand limit. Okay. So we're going to integrate from 1 to t, 1 over x minus 2 dx. I'm going to come over here to the left because I don't have the vertical room to scroll here. So I'm going to take the limit as t goes to 2 from the left of the antiderivative of x minus 1 over x minus 2. Well, that's again a logarithm. And we're evaluating that from 1 to t. So we're taking the limit as t goes to 2 from the left of the logarithm of t minus 2 minus the logarithm of 1 minus 2. That's an absolute value, though, so that's the logarithm of 1. So once again, the logarithm of 1 is 0, so we just have to look at this logarithm. So as t approaches 2 from the left, the absolute value of t is approaching 0, and so this logarithm is approaching, well, in this case, it's going to be negative infinity. Okay, so that integral also diverges. Diverges because the limit doesn't exist. The limit was minus infinity. All right, so these two examples together, I've shown you, well, sometimes you take a one-sided limit from the left. When do you do it from the left? It's when the upper limit of integration was a problem. Sometimes you take a one-sided limit from the right. When do you go from the right? When the lower limit of integration is a problem. Cool. You have to be on alert to watch out for these because sometimes you won't notice that they're improper. I'll show you something about that in a little bit here. All right, this is kind of to complete the story. We talked about integrals 1 over x to the p as x goes from 1 to infinity. Yeah, if I continued this graph, do you remember the story? If we continue the graph of 1 over x to the p for a positive p all has this shape for any p. And maybe you guys remember, I'm not going to write it here, but the integral from 1 to infinity, sorry, this is x equals 1. The integral from 1 to infinity, well, it converged when p was bigger than 1, and it diverged when p was less than or equal to 1. Yeah? So basically, I'm asking the same question, but I want to know, what about this area over here from 0 to 1? Right? This is an improper integral because 1 over x to the p isn't defined when x is 0. So let's see if we can handle this in terms of p. Let's see what the answer is. By the way, we just answered the case when p is equal to 1 in example 2. So in example 2, we saw that it diverged if p is equal to 1. So when I'm computing this here, I'm temporarily assuming that p is not equal to 1. We already know the answer there. All right, so this is going to be the limit as t approaches 0 from the right of the integral from t to 1. I'm going to write this as a power, x to the minus p, for integration purposes. Okay, so that's the limit. As t goes to 0 from the right, antiderivative is, well, you take that minus p and add 1, divide by the new exponent. P isn't 1, so I'm not dividing by 0 there, and I evaluate that from t to 1. Okay, so I got the limit. As t goes from 0 to the right, got my constant out here, minus p plus 1's reciprocal. Plug in 1 for x, any power of 1 is 1. Plug in t for x, and I'm going to write this as a fraction. So I'm going to change the sign of that exponent, put the t downstairs, and write p minus 1. Right? So when you move terms up and down, numerator and denominator in a fraction, you just change the sign of their exponents. All right. So, well, what is this limit? Once again, it's going to depend on p. It's going to depend on p. Because if p is a number, let's start with the bigger than 1 case. If p is a number bigger than 1, then the exponent on t down there, p minus 1, is positive. So if you have a positive exponent down there, then that term is really in the denominator. So when you let t approach 0, well, 1 over 0 is going to go to infinity, right? So this limit isn't going to exist. This limit is not going to exist if p is bigger than 1. And since we already, in the previous example, example 2, we said it doesn't exist if p is equal to 1 either. So you could make that greater than 1, greater than or equal. If p is, well, we're always assuming it's positive. If it's less than 1, then our exponent here, p minus 1, is negative. So this variable t is really in the numerator, right? If it's in the denominator with a negative exponent, it's really in the numerator. So as t goes to 0, that term's just going to vanish. So what do we end up getting? We end up getting our constant here, 1 over minus p plus 1 times 1. And I'm going to write that as 1 over 1 minus p. So that's what we get if p is less than 1. All right, so that's kind of an interesting summary. I'm going to scroll out a little bit so I can keep this, or zoom out rather, so I can keep this visible. But this is kind of cool that if we summarize that on one line, the integral from 0 to 1 of 1 over x to the p, remember, I'm always assuming p is positive here, well, it converges if 0 is less than p, which is less than 1, and it diverges otherwise. That's exactly the opposite behavior of what happened from the integral from 1 to infinity. Do I have enough room to write it here? The integral from 1 to infinity, let's recall, of this same function, it flip-flopped. It diverged if 0 was less than p was less than or equal to 1, and it converged if p was bigger than 1. Yeah, so these things, it's kind of an interesting, let me maybe color code here, the integral from 1 to infinity, maybe I'll shade that area red. And the integral from 0 to 1, it's already shaded black, but let me shade it blue, it looks nicer. So if you put these two things together, I think you should stop the video and think about this for a little bit. But if you choose a p, if this red area is finite, that is p is bigger than 1, then the blue area is infinite. Or if the blue area is finite, p is less than 1, then the red area is infinite. If p equals 1, they're both infinite. Neither one of those things converges. So it's kind of interesting. I like to think about it in the following sense. If the function graph approaches the x-axis fast enough for this area to converge, well, then it can't approach the y-axis fast enough for it to converge, and vice versa. So it's like you can have one, but not both. Okay. I'm going to end here. There's one more well, there's two more examples I want to do, but there's something to watch out that I mentioned before, that improper integrals can be kind of tricky to spot. They're particularly tricky if the point for which the function is undefined is not even one of the endpoints. It could be a point in the middle. So this box over here is telling you how to handle that. If you have some point C in between A and B for which the function isn't continuous, look at the picture, right? You have an asymptote in the middle. Then the integral from A to B, you have to define it as the sum of two improper integrals. Yeah, so you split it at the trouble point, and then you have to take the sum. So you have to look at the integral from A to C. So that's this one. That's where you'd be treating the type 2 integral with a limit at the upper limit of integration. And then you have to add to it the integral from C to B, which is a type 2 integral where the bad spot is at the lower limit of integration. And if both of those things converge, then this thing converges. But be careful. I have kind of a little cautionary example. I'm not proving it here. You prove this, but I claim this improper integral diverges. It's improper because it's not defined at x equals 2. x equals 2, and 2 is in between 1 and 3. So that's what makes it improper. It diverges. I'm going to let you check that. Check out the integral from, say, 2 to 3, for example. Compute it out, and it's going to diverge. So this thing diverges. But watch what happens if I was being uncareful. If I just took this integral and found an antiderivative, that's a perfectly valid antiderivative for 1 over x minus 2 quantity squared. And then if I just evaluated it, what did I do? I just plugged in 3. Okay, 3 minus 2 is 1. And then I plugged in 1. 1 minus 2 is -1, so I'm subtracting -1. So I end up getting the number -2. But this number -2 is nonsense. So where's the flaw in my argument? It's right there. I use the fundamental theorem of calculus in circumstances that I'm not allowed to. F is not continuous on the entire interval from 1 to 3. The fundamental theorem of calculus insists that it be continuous. So the purpose of example 4 is just kind of a cautionary tale. You have to watch out. Unlike type 1 improper integrals, you never miss one, right? Its limit of infinity, or limit of integration is infinity. So you never know, like, oh, that's not a normal integral. It screams out at you, I'm improper. These can be a little sneaky. That's the point of my example. Okay, I think I got one more down here. Oh, I want to talk about the comparison test, sorry. I want to talk about the comparison test. So this is just sort of a discussion for it. So suppose I'm given this picture here. Two functions, f and g. I'm writing some hypotheses over here. So they're both defined on some interval starting at a all the way to infinity. They both have horizontal asymptotes at the y-axis. And like the picture shows, the y values on one of them are greater than or equal to the y values on the other for the, sorry, not a to b, I meant a to infinity. Okay, like in this picture. Yeah, the y values on the graph of f is drawn in blue. The y values on the graph of f are bigger than the y values on that red graph G. So what is my discussion? Suppose that the blue graph is convergent. So what does that mean? That means the area that I'm outlining in blue right now, it never stops. It's an improper integral, but that area is finite. Well, then the area under the red curve is finite too, because it's just a part of it. So that's what my first observation is if the curve that's on top converges, then the curve that's on bottom has to converge because the area is less. Or vice versa, if G is divergent, the area under the red curve is infinite, well, then the area under the blue curve is infinite because it's even more. Okay? So that's what the comparison test says. If you are below a convergent function, then you converge. If you're below a convergent function, like G is below F, then you converge. Or if you're above a divergent function, F is above G, you diverge. Okay? So I'll be quick about this. This is the book statement of it. The comparison theorem is what it's called. And it just says the same thing. You have a couple of functions, they're continuous. One of their y coordinates are greater than or equal to the others. I'm using the same letters. These are the same two remarks. If the function on top converges, then the function on the bottom converges. If the function on the bottom diverges, then the function on the top diverges. So as a last example in this video, let's take a look at how you might use this thing. Suppose somebody asks me to determine if this converges or diverges. Why don't I do it directly? Well, because I don't know how to find an antiderivative for sine squared of x over 1 plus x squared. Right, I've mentioned this before, but antiderivatives are subtle things, right? And I mean, it's easy to write down a function like sine squared of x over 1 plus x squared. I know how to anti-differentiate the pieces, but I don't know how to anti-differentiate this fraction. Antiderivatives are trouble. But if you just want me to tell you, well, does this converge or diverge, I might not need to actually find an antiderivative. Maybe I could just use some comparisons. Comparison theorems are usually a little tricky to use, though, because no one's telling me what to compare it to. I have to choose that. But let me give you an idea. I know that this function is less than or equal to 1 over 1 plus x squared, and let me just write my justification for that down here. That's because the sine, in particular the sine squared of something, is never more than 1, right? So the sine squared of something is never more than 1. And for that matter, the function 1 over 1 plus x squared, that's less than or equal to the function 1 over x squared. How do I know that? That's because 1 plus x squared is certainly bigger than x squared. It's 1 bigger. Well, when you reciprocate, fractions would go the other way, right? Bigger denominators make smaller fractions. So if you like, I'm going to take in my notation of the theorem that's written above there, if I'm thinking of this as the g of x and this as the f of x, then I have the comparison that I want. F of x is greater than or equal to g of x. Well, on particular, the interval from 1 to infinity. It's actually true for all real values of x, but in particular, it's true for the x's in the interval from 1 to infinity. All right. And also, the integral from 1 to infinity of 1 over x squared converges, right? It's one of those power functions with p equal to 2. P equal to 2. If you want me to emphasize it, p equals 2 is bigger than 1, so that thing converges. So therefore, the integral from 1 to infinity of the sine of x squared over 1 plus x squared converges by, I'm going to use an acronym, comparison test. Okay, do I know the value of this integral? No, I don't. But I just know that it's some finite number. So I could pick a large value for b if you like and use some numerical techniques. B, I mean the upper limit of integration. And I could use some numerical techniques to approximate that number, but I know that the number is finite. Okay, that's it for section 7.8. Thanks for listening.